Okay, so what we're going to be talking about is what we call dots. And what dots means here is dots is a difference of two squares. Okay, we're going to call it dots for short, and it means a difference of two squares. Okay, difference means subtract, and then we have two squares. But before we get into that, what we're going to talk about is what happens if we multiply both of these numbers together, or both of these binomials together. These are called conjugates. Okay, so if I'm going to use the area model, I'm going to set it up like this, where I'm multiplying both of those values together. Now, if I multiply x times x, I've got x squared. X times negative 3, I've got negative 3x. X times positive 3, I've got 3x. And then 3 times negative 3 is negative 9. So two things happen here. Number one is when we look at the diagonal, if I've got plus 3x and then minus 3x, that always cancels out. So what we're left with here is x squared minus 9. And what's unique about that is actually the last term, because positive 3 times negative 3 is negative 9. And then x times x is x squared. So if we're going to factor, that means if we're going to break down or simplify or change this into actually what's called a multiplicative relationship, we know that every time I see two perfect squares, I've got x squared, which is a perfect square, and then I've got 9 is a perfect square, and then I've got the difference of the two of them, which means subtracting. Every time I see that, I know that I can simply write this as a product of two binomials, which are called conjugates of each other because it's x plus 3 and then x minus 3. So now, use your calculator to find the list of 15 perfect squares, meaning that in your head, if I write 1 squared, I've got 1, 2 squared, I've got 4, 3 squared, I've got 9. Right, the square numbers here, or the perfect square numbers, are 1, 4, 9. If you want to use your calculator to kind of figure that out, well, we can go right here and we can say, well, y equals x squared. And then you can go to your table. And if we go to our table, we can list, you can see all the numbers right here. I've got 0, 1, 4, 9, 16, 25, 36, 49. All these numbers right here. 64, 81, 100, 121, 144, 169, 196, and then 225. Okay, so those are the numbers that we're going to be looking for. Right, so if you wanted to list them out, you can use your calculator to kind of list them out and figure out what exactly we're looking for. So I'll keep my calculator open to just kind of see that, am I going to find any perfect squares in these problems? So I look at the next example and I notice that, look, there are two terms. There are two terms here. I've got x squared and I've got 144. So if I look over here on the calculator, I can see that right there in the calculator, we've got a value of 12 squared, which is 144. So all we need to do to factor this is simply write x plus 12, x minus 12. That is factored completely. We can't go any farther than that. So that's dots. It's the difference of two squares. Now sometimes if we roll down, you can see here we've got 36x squared minus 25. Now if you notice that all of these values here, all these numbers, are actually perfect squares. 36 is a perfect square, and then we've got 25 is a perfect square. We're subtracting, which means a difference, and we also have x squared, which is a perfect square. So what I'm going to write is, now I know that it's going to be a product of two binomials. In this case, we've got 6x plus 5 and then 6x minus 5. And then we're done. We're finished with that. If we wanted to multiply that back out, just like we did in the beginning example, right? If we wanted to multiply that back out, you can see very clearly that the middle terms will always cancel out if it's laid out in this particular order. Okay? Now, moving on to a couple more examples as they get a little bit more challenging. Things you need to be concerned about is making sure that you have the order correct. So if I look over on my calculator here, I've got 9 is a perfect square. The square root of 9 is 3. And if I go to 64, 64 is also a perfect square, right? Because 8 times 8 is 64. So I've got two terms. I've got a difference, which I mean subtracting. So I'm going to write 3 plus 8x, and then 3 minus 8x. And then we're done. And again, if we multiply that out, the middle terms would disappear. The middle terms would disappear. And let's keep scrolling. Let's check this one out. 81 minus 4x. So if I go to 81, the square root of 81 is 9. And then if I go to square root of 4 is 2. So if I'm going to factor this using the difference of two squares method, the square root of 81 is 9 plus 2x, 9 minus 2x. Now these are equivalent. If I wrote 9 minus 2x, then 9 plus 2x, you would still come up with the same exact answer because multiplication is commutative, meaning that you can switch it back and forth or left and right. 3 times 4 is the same as 4 times 3. Okay? All right, moving on to what happens when we have higher powers and then a variable by itself. So numerically, we can see, well, 121 is a perfect square. The square root of 121 is 11. So I know for sure I can write, well, I know I got 11, and I know I'm going to have 11. Now, the square root of x squared, or x to the fourth, is actually x squared. And the square root of y to the fourth is actually y squared. So all I need to make sure that I have in between is both a positive and then a negative y squared. And why does that happen? If you think about it, the last time that I multiply, if I were to multiply this back out, a negative y squared times a positive y squared would be a negative y to the fourth. And you can see that's right there. And if I multiplied out the first terms, 11 times 11 is 121. And then x squared times x squared is x to the fourth. And you see where that comes into play. And then if I multiplied out the middle terms, they would just disappear. So that's one way to certainly check your answer. And again, looking into another example right here, we have 9x to the sixth, y to the fourth, minus 1. Now 1 becomes a little bit of a tricky number because 9, the square root of 9 is 3. But the square root of 1 is 1, as you can see in my calculator. So I'm going to separate this and break down each part. So the square root of 9 is 3. The square root of x to the sixth is x to the third power. X to the third power. And the square root of y to the fourth is y squared, and then y squared. Now, what's interesting here is I know I'm going to be adding, and I know I'm going to be subtracting. The square root of 1 is 1, and the square root of 1 is 1. So I'm going to leave it just like that. And that's it. So DOTS becomes a pretty simple method if you're really, really, really thinking about it. Because what you have here, you have two terms and you're subtracting. So anytime you have two terms and you're subtracting, check to see if any of them are perfect squares. And if you want to check it to see if they're perfect squares, in your calculator, write y equals x squared, and then click on the table button, and then you'll have a list of all of them right here. All right. Hope all is well. Good luck.